the signal strength. So we have to understand the concept of signal strength. It means how you strongly drive the output node. For example, the strength is determined by the resistance. For example, we have a voltage source VO. You want to drive a certain node with certain voltage, like with the resistance R. So if you have like smaller R0, then so let's if the R0, then the output will be the same as the voltage source here, no matter what you have on the output load. For example, if you have in this case Vout equal to let's say Vout equal to RL plus RL VO, like that. So no matter what is, for example, R equal to infinity, we have a Vout equal to VO. But if the RL is similar to RL, then Vout is equal to half VO. So originally we wanted to deliver VO to the output. Because of the load condition, the output would not be what you wanted to drive. So for the strongest strength would be R equal to 0 case. This is strong driver. This is strong voltage driver. So we have a supply voltage VDD and ground that is the strongest 1 and 0 because it has its own. It doesn't have any resistance there. We assume the ideal voltage source. So we have a supply voltage VDD. Supply voltage passed through the PMOS to the output. Let's say VDD. So also have a ground voltage there, VGND, that is passed through the MOS switch. This is GND, 0 volt. Depending on the resistance of each transistor, signal strength is determined. So far we just assume that each switch transistor, when it is in triode, we assume there are on tunnel resistance is 0, so it is driving ideal voltage. But in reality there is some limitation. For example, when you want to drive the output to VDD, you use the PMOS, and pull down you use MOS. In this case we can deliver very good VDD or 0 to the load. But what happens if we swap the device type from the VDD and GND? We use like that. For pull up we try to use the MOS, and for pull down we use the PMOS. Then let's say the output, the MOS trying to deliver the load current to in this direction, so the drain and source is here. So we always care about VGS here. for the given current direction, so the transistor is on only if VGS greater than VTH. Once the VGS close to VTH, it will be turned off. So the maximum pull-up VO max is limited, output voltage is limited by VDD minus VTH. Similarly, for the pull-down, VO min is limited to 0 plus VTH of the PMOS. So PMOS, we have a source here, we have a source and gate. So VSG, actually what it determines the behavior of the transistor. If the VSG when it trying to pull down the voltage drop, and that is close to VTH, then VSG become VTH of the absolute. So absolute VTH there, then the PMOS will be turned off. So the maximum and minimum voltage is quite limited compared with the ideal case of the proper use of the transistor like that in digital. So we define those two stages. So we can MMOS can pass this 0 very strongly, but MMOS cannot pass 1, logic 1. So we drive the weak 1, or the output is degraded. We can say that the PMOS can pass the VDD properly with the strongly, but the output for the 0 is degraded, meaning the output cannot be pushed down to 0. It always is some limitation. So we know that from this fact, MMOS is best for pull down and PMOS is best for pull up network. So we will look at now the pass transistor characteristic. We know that for MMOS, if the input is 0, then open. Input is 1, we say that this is closed. But one thing to note is that for MMOS, the 0 passes strongly. The 1 cannot pass properly. It only has degraded in the output. This is because, let's say, for example, if you want to pull up, let's say this is VDD and VDD, this is capacitor there, the current need to flow from left to right. This means that this becomes the source. Right hand side is source and left hand side is drain. So there is always, for this transistor to be on, VGS must be greater than VTH. So the output, when it go up, the maximum voltage it reaches only VTH here. On the other hand, when the MMOS is trying to drive the 0, this is, let's say 0, I'm sorry, this is VDD, then output load is driven like that, the current direction is like that, the source node is on the left, drain is on the right. So output load can be easily driven to 0 because there is always VGS greater than VGS is already VDD, so this is greater than VTH. Similarly, for the PMOS, the input is 0, it's trying to let's say this is 0, this is VDD, then we know that trying to, the current direction is like that. So this is the source and this is gate and this is drain. So VSG is always greater than VTH. So the drain voltage can go up to VDD. But when we trying to pass the zero again, the current need to go down to from the left to the right to the left, from the right to the left. So this is the source and drain. So this is the zero. So VSG. So this one goes down, let's say initially charge the VDD. We want to discharge to zero, but when this goes down until VTH level, then transistor becomes turned off, so it cannot pull down anymore. So final voltage become VTH instead of zero. So that's why we say in this case output is degraded. If you think about what would be then the ideal switch, MOS only capable of driving zero properly, and PMOS is capable of driving VDD properly. So, but for an ideal switch need to pass both 0 and 1 well. So, possible solution for the ideal switch will be transmission gate by adding two transistor in parallel, like that. The control signal we will have with the inverter, like that. So enable X and Y, something like that. So if you want to pass if you want to connect X and Y, then say assert the enable to VDD. To summarize, the passed transistor by itself produce a degraded output, so we have to use transmission gate that passes both 0 and 1 well, something like this. Its symbolic representation can be this and this or that. So I prefer to use this symbol because it shows some both direction, like that, and control bubble control, something like that. Okay, either this or that will be mostly popularly used convention. Tri-stage, sometime we want to make the output high G, I mean not floating. So when the output when this kind of a control, if the enable signal is asserted, we want to pass the input to output, and 0 and 1. But if the enable is 0, the output become the high impedance, meaning floating. Floating is something is a state of not driven electrically, so the voltage is not well defined by itself. Only the external driver will drive that node. This is kind of used something like a bus structure. used in bus. For example, let's just share the single line, multiple driver attached to it. So enable 1, enable 2, enable 3. So whatever x, y, z, x1, x2, x3, and y. So anything that enabled that will drive the output load. When the disabled output is high impedance, meaning open circuit. So in transistor, we can draw this function something like this. So the output, to make the output floating, we have like that. So this is enable bar, input connection. So this is A and Y. So whenever the enable is activated and pull up and pull down, networks are enabled and connected to the output. Okay. So something like that. I already talked about this. Now the transmission gate also, it can act as a tri-state buffer, as I showed you before. A little different. Yeah, there are two. So previously I showed that tri-state buffer like this. Enable bar, inverter, Y. So if you make a connection between here and there, it becomes a tri-state. It also tri-state buffer. Looks like inverter, two inverter there, and pass transistor gate. This is another way of implementing tri-state buffer. But difference is, we may learn later, each transistor has parasitic capacitance at the source and drain, because we have the diffusion. Each transistor has just, and let's say for MOS P substrate, we have a reverse biased diode. It has a parasitic depletion capacitance. So each transistor have the parasitic capacitance there. So if you, without this, so for the pull-up network, it only need to charge and discharge. Pull-up network, we need to charge this and this, that, right? So we are not seeing, let's say, we are not seeing this capacitance strongly. I mean, this node voltage doesn't go to VDD, so we doesn't need to charge up to VDD for this parasitic. So, but in this implementation, we have to charge the older. If we connect between those two, all those internal parasitic need to be driven to VDD or ground for the case of the pull down. So it slows down. So most of the case we prefer not to add this kind of a connection in the tri-state buffer. You can see the speed difference in simulation. Another one thing that we have to know is that this is non-restoring path transmission gate is non-restoring, meaning any noise onto, let's say, either VDD or ground, any noise onto the signal will pass to the output, right? But in the case of the inverter, let's say inverter case, when you pass the signal, so here 1 and 0, noisy signal comes in, but we use the internal clean supply, so output will be clean at the time internally, and the final output will be also clean, like that. So this is kind of this is restoring the signal, but transmission gate is not restoring properly. It just passes the noise as well. So this kind of buffer has the restore the output, because the any noise on the input will not pass. Just ignore the polarity of the input. This invert the inputs, so but use the supply and ground to restore the signal level. So this series connection on both PMOS and NMOS violates the complement rule, but we ensure that those two switches never turn on. Those switches can be both turned off at the same time, so make it a Z output, floating output, by having this kind of inverted control and enable signal here. So this can be simplified into two states. One is high G state and one is inverter state. So it's a symbol, can be like this. So enable comes in, and for this representation we have a bubble. So enable bar will make this one in buffer enable. This is multiplexer. So depending on the selection signal S, we select the output. So Y, if the select signal is 0, then D0 pass to the output. So if you write the in Boolean equation, Y equal D0 when S becomes 0, or so when the S is high, then we pass the D1. So we go to 0, so 1 goes to 1, and this 0 go to 0, 1 go to 1. So X means the don't care. We don't care about what the D1 is if S is 0, right? Because D0 go to the output. Okay, so symbol, we draw symbol like that for multiplexer. We filled in like this. So how we make this kind of a multiplexer in gate level, and how many transistors will be needed. For here, we can draw the AND gate and D1 and D0. So this is the selection. Inverter selection, like that. OR gate, right? So if the selection is 0, then this become 1. The D0 pass to the output because the output here is 0. The OR gate doesn't pass the other side, right? So we can build a system like that. So how many transistors we may need for this kind of operation? So you can use some bubble pushing technique, or we can just draw that as it is. So AND gate, we can draw that NAND gate plus inverter, right? So OR gate is OR gate NOR gate plus inverter, right? So if you count the number of transistors for the inverter, we have 2. We have here AND gate. So this one 2, 1, 2, 3, 4 plus 2. So 2 inverter plus 2 inverter so we have a, let's say, how many inverter we have? 2 times 1, 2, 3, 3 plus, for the NAND gate, we have a 2 NAND gate there, 2 times the number of number of NAND. How many? Number of I'm sorry, we have to start from beginning. So total inverter, how many number of inverters? So inverter 1, 2, 3, 4 inverter, right? 1, 2, 3, 4. Now NAND gate, how many NAND gate? We have 1, 2 NAND gate. How many NOR gate? We have 1 NOR gate. So number of transistor, how many transistor for inverter? We have a 2 transistor. For NAND gate, we have a 4 transistor. NOR gate, we also have a 4 transistor. So if you multiply and all add up, 8, 4, so we have a total 20 transistor. So it's quite so many transistor we have to implement gate level multiplexer. This is the answer. We need 20 total transistor, right? We'll move, so this symbol same as inverter, right? So the bubble means just inversion. Now we can use some transmission gate to implement the multiplexer. We will see how we can make it in the next slide. So by having this kind of arrangement, we can implement the multiplexer. Considering we need to generate the S bar through the inverter, we need total 4 plus 2, total 6 transistors. If the S bar is available, then only 4 if S bar is available from the input. If not, we have to add inverter, so total 6 transistors. So if you compare with the previous gate level implementation, this is a lot smaller transistor. This is a very efficient way of making multiplexer. But the problem, one of the issue we mentioned before, this is non-restoring, meaning any input glitches or noise will pass through the output, right? Inverting multiplexer. So in this case, there's several way of implementing multiplexer. The one is to use compound gate, AOI. The term we use the compound gate here. The compound gate is kind of a single CMOS stage, and implementing this equation like y equal d0 when s bar is done, and when the s is coming, then we pass to 1. So this kind of selection need to be done, but for the CMOS circuit, we prefer to have something like that equation. Above the equation, we want to have the bar in it, because we typically implement the MMOS tree first. So this MMOS pull down path is made out of from this equation down here, and this is series connection and parallel connection, and converted here to parallel, and to parallel, and also series connection between two parallels as well. So this is kind of complementary logic to easily construct the construct that the compound gate we prefer to represent the logic in this format. So another way is to use a tri-state inverter shown here. So depending on the selection signal, the output passes the input to output. When the selection is not selected, then the output is driven to the high Z state. So selected buffer will drive the output. A third one is using the path transistor. Use the transmission gate like that, right? Like that. So, but the transmission gate doesn't have an inverting function, so we have to add inverter at the output to construct the inverted output. Okay. Now let's construct the default 1 multiplexer. So we have incoming 4 signal D0, D1, D2, D3, and depending on selection signal S0, S1, we select 0, 1, 2, 3. 0, 1, 2, 3 means when S1 and S0, 0, 0, 0, 1, 1, 0, 1, 1 cases, right? This is D0, D1, D2, 3 for the output Y. How we are gonna make it? In the previous slide, we just looked at 2-to-1 multiplexer. Can we use 2-to-1? Let's look at it in the next slide. Here we have 2 stages of 2-to-1 multiplexer. Be careful about how you control those connections. You first one select the 0 between 0 and 1 and 2 and 3. One of them passes, and then final S1 select the output. So this kind of a 2-level of 2-to-1 multiplexer can be implemented to implement 4-to-1 MUX. The other way is to use tri-state buffer. So whenever on the right hand side, so only single stage tri-state buffer is there. When that is enabled, we pass that to output, right? But we have to have some kind of a decoding logic, decoder, to have in this decoding we require like the AND gate and inverter. So for 0 0, so selection 0, this is selection 0, selection let's say, I'm sorry, this is 0 this is 0 0, this is 0 1, and this is 1 0 and 1 1, right? Then it's selected. So we can construct the AND gate. 1 1 means the last one is selected, and something like that. 1 1 0 1 and 1 0 0 1 1, and what else? 1 0 and 0 0. Then enabled, right? EN 0, EN 1, EN 2, EN 3, something like that, right? So this is EN, let's say this is EN 0, EN 1, enable 2, enable 3, like that. So it requires some kind of a decoding stages to minimize the number of stages in the data path, right? This is something that you can think of. One penalty for that is the output node. There are so many devices, 4 buffers are connected, so it all has a very heavy parasitic capacitance, because each transistor has a source and drain capacitance from the reverse junction diode. We call it like a diffusion capacitor. So that's the penalty.